Welcome to this topic, Introductory Electronics. We're going to discuss this topic in the following manner. We're going to start with a concept of emission of electrons. Then we'll get to take a look at an application of emission of electrons called cathode ray oscilloscope. Then after that, we'll take a look at some other ways of measuring voltage using the same cathode ray oscilloscope. Then we'll end with the ways of measuring time using the same cathode ray oscilloscope. So we start with emission of electrons. So an electrode is a metallic conductor which is in contact with non-metallic parts of the circuit. So normally circuits are made of wires, a battery, a wire, and maybe bulbs and the likes. But we have situations where we have wires which are metallic conductors, then at some point we won't have a wire. So the part of the wires which are metallic conductors which are in contact with parts that are non-metallic are called electrodes. So there are two types of electrodes. There is what is called a cathode. A cathode is a negatively charged electrode, or an electrode that is negative is called a cathode. Remember, any circuit has a positive side and a negative side. So the part that is negative is called a cathode. Then the anode is the positive part. So now it has been observed in nature that hot surfaces emit electrons. This emission of electrons from a hot surface is called thermionic emission. So this topic actually is based on this concept of thermionic emission. So when we have a circuit which is powered by high voltage, and on one end of the circuit, if we have an anode and the other end a cathode, this high voltage is going to somehow hit the cathode and the anode. So if these are connected, not connected, there is space here, so they're not connected. So if these are arranged like this, then between them, if there is a vacuum, so this tube here is a vacuum, it is connected to a vacuum pump so that we suck out all the air inside. We remain with no any state of matter, no solid, no liquid, no gas. So when we have a vacuum here, and then when this circuit is powered, it has been observed that electrons are going to be emitted from the cathode, which is negative. Remember, electrons are negative, so when the circuit is not powered, they are abundant here on the cathode. So when they are emitted, the electrons are going to flow to the anode. Why are they flowing to the anode? First, because electrons are negative and the anode is positive, and like charges repel. Remember the law of charges. The second is so that, of course, the circuit is complete. So these electrons that flow are called cathode ray. So now we're going to take a look at characteristics of these electrons. So before we can even take a look at this diagram, we're going to start from the top. So the first characteristic of an electron is it has a smaller mass than a proton or neutron, as we learned in chemistry. An electron has a smaller mass than a proton or a neutron. Secondly, cathode rays, which are streams of electrons emitted from the cathode going to the anode, travel in a straight line. Just like light, they travel in a straight line. When a magnetic field and an electric field change the direction of cathode rays as below. So when you put a magnetic field somewhere where the cathode rays are passing, they're going to be deflected like this. And when you put an electric field, they're going to be deflected towards the positive, since electrons are negative, and they would be attracted in a way to the positive side of the electrical field. Finally, electrons are negatively charged, as we know, so that they attract, or they get attracted to the anode. So this is the point that I emphasized on why electrons flow from the cathode to the anode. Now, because of this, usually when we are studying electricity, we assume that our current moves from the positive going to the negative. Okay, that's how we take it. But in fact, if current is the movement of electrons, we are wrong. Okay, so we always think power moves from the positive going to the negative, and we assume that the current moves from the positive going to the negative, and we assume that's the direction of electricity. But in actuality, electrons move from the negative because that's where there are plenty, then they go to the positive. So the direction of flow of electrons is always opposite to the direction of current that we usually use when studying. So this direction of current is just something that people have come to agree upon, that the direction of current is going to be from the positive to the negative. Otherwise, the actual movement of electricity is from the negative to the positive. So since this is not what actually happens, but what people have come to agree on, it is called conventional current, something that people have agreed on. Now we look at this device, which is created based on the concept of thermionic emission, called a cathode ray oscilloscope. So a cathode ray oscilloscope has three main parts. So the first part is called the electron gun. So the electron gun is the part from here to here. So the parts that makes up the electron gun are a filament which provides heat, then there's a cathode which gets heated and emits electrons, then there's this grid which I'm going to explain the function, and also these two which makes up the anode. Then the deflection system is made up of these two pairs of plates. The first pair are called Y plates, then the second pair is called X plates. Then here there is a screen called the fluorescent screen. So these cathode ray, if you remember those old TVs that had glucose, for those who can remember, they were made from this technology. So this is what used to constitute the glucose. Then but this cathode ray oscilloscope, it is usually found in the lab, a special electronics lab, to just measure various things, as we're going to see. So here in front there is a screen, just like that TV there was a screen. So even these ones, there's a screen here. So this screen is what is called the fluorescent screen. So three parts: electron gun, deflection system, and fluorescent screen. So now what do each of these parts do? So I'm going to use this illustration. I'm going to draw two electrons. So the filament provides heat to the cathode. Once the cathode is heated, it's going to emit electrons by the process of thermionic emission. So once electrons are emitted, they are going to go to the grid. So they will move to the grid. Once they reach the grid, the purpose of the grid is to adjust brightness. So to adjust brightness, what it means is sometimes you depending on your site, you might want what you see on the screen to be brighter. So you have access to a tuner which you are going to tune to choose the level of brightness. So once you do that, when you tune, this is going to be adjusted in such a way that if you want your screen to be brighter or image to be brighter, it's going to allow more electrons to pass through it. But if you want your image to be less bright, it's going to allow some electrons and it's going to block some electrons. So that's the purpose of the grid. So in this case, only one electron is going to pass, just for illustration here. So one is going to be blocked, so that you remember that this has the power to block if brightness has to be reduced, or to allow as many as it can if brightness has to be increased. So that's the purpose of the grid, for brightness adjustment. So you should be excited. We're studying how TV works here. So the next is the anode. Remember, in the illustration I'd given of a cathode and an anode in a vacuum. By the way, this whole thing is a vacuum. We have a cathode here and we have anodes here. So these anodes are designed such that the electrons will be forced to move in between them, okay, at the center of the anodes. That's why they're cylindrical, so that the electrons are pushed to move in between them. Don't worry about how the cylindrical structure makes them to move in between them. Just know that the job of this is, one, to make the electrons forecast so that all the electrons are closer, and of course they can produce the image that's supposed to be produced, and also to accelerate the electrons. So they forecast and accelerate the electrons by the way they were designed. So this is what the anode is going to do. Sorry for the noise. Where I am, there is a train passing, so yeah. So after that, there is what is called now the deflection system. So the deflection system of two types. There is the Y plate and the X plate. So the Y plates, the job is, let's say you have this image but you want to take it up or down. So the job of the Y plates is to deflect the electrons up or down. So this is going to deflect the electrons up or down. Then the X plate, if you want to push your image to the left or to the right, so the X plate is going to deflect the electrons left or right, like this. So the electron has to pass in between. I did not do my animation very well. The electron has to pass in between these two plates. So let me just summarize the function of everything, and of course the function of the screen is just to display the image. So I talked of the filament, which heats up the cathode which emits electrons by thermionic emission, the grid, which is for brightness control by controlling the amount of electrons passing through it, the anode, which focuses and accelerates the electron beam. The cathode ray is also called the electron beam, of course. Y plate is, of course, for deflecting the electron beam up or down. The X plate for deflecting the electron beam left or right. Then the screen for displaying waveforms. So the images you're going to see are waveforms. So next we're going, I don't know what this worm is doing here, but anyway, the two applications of the C.R.O. is first, measuring voltage. So the C.R.O. can be used as a voltmeter. It can measure both AC and DC voltages. So there are two types of voltages, just like there are types of currents, alternate current and direct current. So for voltages, we have AC voltage and DC voltage. So this can be used to measure both. DC voltage is not difficult to measure, because when you put DC voltage at the input of this equipment, you are going to see a single line pointing at a single number, for example 5 volts or 10 volts. But for AC, you're going to see a wave like this. So how do you tell the voltage? Because you have a scale here, which for example might be 0, 1, 2, 3, 4, 5. So how do you tell what voltage is this? So this instrument measures what is called peak voltage of AC input signal. So peak voltage is the voltage at the top of the wave here. So it will tell us what the voltage is here at the top. Now there is a tuner which is called the which can be adjusted. So the Y gain of this tuner, or the Y gain setting, will indicate the voltage applied, or that needs to be applied, in order to deflect the beam by 1 centimeter on the screen in the vertical direction. So this might be difficult to imagine, the fact that you haven't seen an actual C.R.O, but you're going to see in an example. So just to add more light, if Y gain setting is 5 volts per centimeter, so if the tuner you have selected 5 volts per centimeter, what it means that 1 centimeter of the height on the screen will mean 5 volts of the input signal. So let's take a look at an example. The diagram shows the screen of a C.R.O. Y gain setting is 3 volts per centimeter. What is the peak voltage applied to the Y input of the C.R.O? So this is the skin of the C.R.O. So they have said the Y gain setting is 3 volts is represented by 1 centimeter. Then here, if we see there are 3 centimeters, so many volts here. So what it means here, it means since I've said 1 centimeter is 3 volts, so we're talking about 3 volts, 6 volts, 9 volts. So this 3 centimeters is 9 volts. But of course, we can use mathematics to help us to deal with complicated numbers. So with mathematics, we can say the Y gain setting is 3 volts per centimeter, which translates to 3 volts is equal to 1 centimeter. Okay. Now, how many volts are going to be equal to 3 centimeters on the screen? Because our peak voltage is what we're looking for. So we do what is called cross multiplication, where we multiply this and this and this and this. So x times 1 we're going to have x, 3 times 3 we're going to have 9. So we're going to have 3 times 3, which gives us 9 volts. Finally, another application of the C.R.O is measuring in short time interval. So the C.R.O can be used to measure short time intervals. In this case, we have a tuner where we can select the time-based setting. So the time-based setting indicates the time needed for the light spot to sweep through 1 centimeter on the screen in the horizontal direction. So for time, it's from left to right. For voltage, it's up, down. So again, just to add more light, if the time-based setting is 5 milliseconds per centimeter, it means that 1 centimeter of the horizontal length on the screen shows 5 milliseconds. Okay, so 1 centimeter will be equal to 5 milliseconds. So let's take a look at the last example. The diagram shows the skin of a C.R.O. The time base is set to 5 milliseconds per centimeter. What is the period of the input AC signal? So they have used the word period here in an effort to confuse us, but period, of course, we're just talking about time. In short, it is what is the time of the input AC signal. So here we have the screen. So they have said the settings are 5 milliseconds corresponds to 1 centimeter. So here we have 1, 2, 3, 4. By the way, the reason they have used period maybe is just to test our understanding of waves. So what's the period here? The period is when the wave repeats itself. So if it's starting from here, then it will go like this, then here it's when it is repeating itself, which is this 4 centimeters, which they have already measured for us. So we say the time base setting is 5 milliseconds per centimeter, which translates to 5 milliseconds equal to 1 centimeter. What about 4 centimeter? So 4 centimeters is going to represent what? You forgive me here, I was supposed to write this down here, but then we're going to do cross multiply. X multiply it, we multiply it with 1, 5 multiply it with 4. So we're going to have x times 1, x, and 5 times 4, which is going to give us 20 milliseconds. If you want to convert milliseconds to seconds, just divide by 1000, if you remember, and you're going to have 0.02 seconds. So this is how to deal with interpreting the readings on a C.R.O. Happy solving.